Today we talk about another tree structure, right? We will talk about Splay Trees. Okay, so you already know, of course, the regular binary search tree, right? Which can degrade in performance if you have a wrong order, basically. You know, if it's not random, it's ordered, you have a problem. So for that reason, we have AVL trees, we have red-black trees. So then why would you need anything else? Well, in mid-80s, this is like almost 40 years ago, so almost ancient history, but still more recent than 60s, right? Two pretty famous algorithm designers, let's see what their names are. Slater, no, this is not Slater, Slater and Tarjan, right? Pretty big names in data structures. I think they were working for AT&T at the time, right? They came up with this idea that why would you need this, right? Basically, if some data is more likely to be accessed more often than other, basically, right? You have some structure, right? And you want to pull out some data, right? So they come up with this idea of, again, self-balancing, or you could say sort of balancing. It's different. It's not maybe balancing, but it's more like the things you get more often, they are going to be quicker. So basic idea is things will stop. Some will keep the most frequently accessed data items at the top of the tree, so they can be accessed quicker. And what's cool thing is they prove that amortized, meaning on average, it will still be log n, right? So if you have completely uniform access, this is not a structure for you. But in real world, this access actually is quite useful, actually, right? Meaning, let me show you where's my big old cheat sheet here, right? So you check here, Splay tree, right? Log n, log n, log n, log n, log n, log n, right? So again, has similar performance as a red-black tree and AVL tree, but it is amortized, meaning, well, some operations will be slow, relatively. The ones the data you access rarely, right, will be kind of slow. But immediately, if you keep accessing the data, it will become very quick, right? So if you completely access data randomly, completely, right, you just pick something, right? This is not a structure for you. But if you tend to access things more in some sort of pattern, this will be a really cool structure. And the way it works really cool. It's a really cool structure, and I'll show you how it is, right? So let's see this in action, right? Let's see this in action. So let's insert 10, right? Insert 10, right? So let's insert 12, right? What do you think is going to happen? Well, any operation counts. Insertion or access counts as well as basically as using this data, right? So this means that this 12 should be at the top. Let's take a look. So if you do it 12, what does it mean? 10 will be to the left of it, right? Yeah. That's what should happen. You see? So 12 is left. Okay. So now I will insert, I don't know, whatever. I'll insert 14 or something, right? So in this case, right? It's still, so now you get a linked list. So it's, okay, that's not so good, right? Because I'm doing it in order. Let's say insert 8, right? But 8 has to be at top, you see? So it's kind of cool. So basically, the last insertions are at the top, basically, right? Even now, right? So if I keep inserting, let's insert 16. So it's going to be 16 here, right? But is it going to stay here? No, it's going to go up top, right? It's going to go up top. And look at this, right? Now again, we got back kind of bad. So again, the initial performance will be kind of bad if you do it in ordered setting, right? If you do it random insertions, it will be really good immediately. But let's do one more. Let's do like 6, right? 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 So it looks really weird, right? So keep inserting. Let's see what can I insert. Let's say because I'm inserting. Well, I'm doing the worst thing possible. Let's insert. Yeah.
11.
11 exactly. Let's do 11. So first of all, where should 11 go? Not here. Here, right?
Yes.
Yes. So it will keep going, right? Now it has to go more up, right? 1, 2. Cool. You have this nice little design now, right? So again, so notice again. So the things we insert first, 10 and 12 at the bottom, right? The recent ones are very quick to access, basically. So can you imagine where this is good? It is, of course, for any type of caching situation. type of structure will be useful, right? So, again, so 11, right? So what can we insert now? Any number?
5.
Which one?
5.
5. 5?
Yeah.
Okay, 5 should go here, right? So it'll move up. And again, it has to move up, right? So weird, right? So can we do 11? Let's see, 15, right? 15. Oh, sorry, it's there. 15 is there, right? Yeah. So it looks kind of chaotic, right? But overall, right, the top, right, the things which are the most frequently accessed will be at top. So so now let's find something, right? So what should I look for? I'll look for 11, right? If I look for 11, we can find it, right? But now it's at top, right? So if I look for 11, of course, nothing happens, right? So that's the only operation. Looking for a root value, nothing will happen. But if I look for 15, right? So looking actually modifies the structure, right? 5, right? So if I look for 10, let's look for 10, right? That's basically the bottom, like rarely used. Right? So again, it keeps rotating and changing, but again, so this is obviously it's not going to be as balanced, right? But again, this funny thing is overall, right? It is going to still be log n, right? So you gain a lot from these frequent accesses like the top, right? And then you lose some. Occasionally you have really bad access for like 12, right? Because again, the theory, the idea is okay, you maybe don't need this 12, but then once you start using it, you'll need more and more of this, basically, right? We look for 12. Now the question is, can we figure out what's going to happen is 12? It's probably going to be up here, right? So I think it's going to be here, no, here, and then 11 there, I think. Let's try to see if we can do this. So obviously 12 has to go up. 1, right. So again, it seems you see only it's almost like a linked list, right? It doesn't seem like deficient, right? But again, it depends what we're looking for. Again, so if I keep looking for these 3, right? Like if I look for 14, obviously, right? And if I look for 11, right? Keep going back and forth, right? So how about 8? Yeah. So you see, I'm gonna get somewhat look like 3 looking. Yeah. Okay. So that's a big idea, right? So how do we accomplish this? So you saw this already that there's almost constant change, right? So we do what we call it, what these creators they call it splay. I don't know how to translate this in Latvian. Splaying is like, well, I guess the word is from where it came from, basically, right? So Splay Trees, as we saw this, I already showed you, right? The worst case find, insert, delete is linear, right? Because of course you saw it looked kind of linear, right? But they guarantee if you do m operations on a Splay tree with n elements amortized, right? It's m log n, basically, right? So red-black trees, AVL trees, m log n, because we know, right? So basically again, since always if you keep doing these most recent accessed items, right, you will be basically getting small, well, it will still be amortized log n, but it will be quicker than red-black trees and AVL trees. So there's no explicit balancing mechanism. It's implicit, right? It sort of happens. So I think it's kind of cool, but again, of course, it's not always needed, right? So splaying is like spread. I think it's from some sort of, where did it come from? Splaying. Let's see this little calculation. Splaying. What does it mean? Actually, kind of weird. Splay. It's like his legs spread out in front of him. I guess, yeah, spread out basically, right? So spreading out. There's a medical term, I guess, too, right? So there's going to be a splay operation, basically, right? So as we search for something or insert, so insertion, deletion, right? Well, I guess let's look at deletion in a moment. What happens if we delete something? Let's delete 14. Delete 14. What will happen? Probably nothing. Just going to delete, I think. Let's see. Or I think actually might still change something. Deletion. Oh, it moves up top, right? And then, so moves up top and then delete. Okay. Now, so, and again, now, so I think deletion actually leads to more sort of like makes your tree actually look like you know, more like a tree than two lists basically.
Where on the practical level splay trees are used?
Like I said, anytime caching, like if you don't use hashing structure, right? But for cache, right?
Yeah.
When you expect things to be at some would be in bunches basically, right? So like could use I forget some database used also for some sort of indexing, some sort of like extra solution from what I read. I believe Redis uses it if I remember correctly. I believe somewhere there's some case. Let me do just quickly, which is one of the big major Redis Splay Tree. I think it was. Yeah, I think so. Oh, no, they used rope. I think they used something else. But yeah, but they used something. Yeah, yeah. There's couple things where it's used. They use some. They don't show it, of course. It's underneath, right? It's written in C, right? So.
But the goal of this structure is kind of to sort it in a way that the most frequently accessed elements are at the top. But deletion in that case doesn't make really sense because then it pulls the 12 and other elements that are not as frequent.
Yeah, no, the basic idea is this, that you will not be accessing, if you, again, you lose out on all the benefits of this if you access elements roughly equal, right? If you know, you take 8, 6, 15, 12, right, roughly equal time. But if there are some elements which you need more often, right, then this tree will provide the performance benefit, right? Because that's the basic idea, right? So it's yeah, question?
But the worst case scenario is like really bad, right?
Well, yeah, I mean, no.
It's like it can become a line, if I understand.
Yeah, basically, the worst case scenario is if you completely randomly access data in a Splay tree, then it becomes bad, basically. But they said, but that's the funny thing, okay, I say bad, we saw it looks bad, but they proved it, actually, even in the worst case scenario, if you completely randomly access data, right, it's still amortized to this m log n. So the question is, you can't even make it unless you like, you know, always know which is the worst one to pick, right? Right? Then yeah, if you always pick the one the least, okay, if you know you have this genie telling you which one is the least used, which one's at the bottom, right? Then you will be basically breaking this tree, right? But the idea is on a random access, meaning if you completely randomly, on average it will be still log n, right? On average, right? If you have some specific preference, it will be better than actually log n. It'll amortize log n, but smaller constant. But only if you could somehow always pick the least used, right? So if there's some situation where it's always like you don't, you pick the numbers which are least used, then it will be, really bad, right? You pick 10, you pick 6, right? Of course.
Yeah, we can make it like a linear.
Yeah, again. So that's the thing, right? So let's see if you can let me renew. Let's see if I can make something really bad. So let's do 10. First of all, if I insert in order, right? I'll do 12, right? Of course now. So if I do 14, what's going to happen? It's going to go here, right? Of course, right? You have a nice linear. 16, right? So looking quick. Again, remember this is insertions quick. I mean, it looks bad, but insertion was quick. And if I need 18 now, right? The one I inserted recently, it will look still good, right? So 20, right? So looking like this. So now the worst case scenario is of course 10, right? Because I'll need 1, 2, 3, 4, 5, right? So if I do 10, right? Find 10, right? So this is the worst case scenario. I know, okay, I need the first item, which I insert first, right? So, but look at this here, actually, getting the last, actually, right? I created kind of tree structure out of this, actually, right? So next time I need 14, it's not going to be so bad, actually, right? So not the thing that proved, actually, even if you try to break it, it's not so easy to break it, basically, right? It's still going to be this m log n, actually, right? So worst case scenario, right? So 14, right? 14 is going to be top, of course. Okay, and you see again we have something. So again, it will look sort of like tree even if you try your worst, right? So once you start playing, you spread out, right? You will end up with some structure. So it's again obviously not as nice as AVL and red black trees. So again, some cool ideas. Again, not of course. Obviously, this is considered a graduate topic, right? But you guys are, but you guys are smart, right? So it's not that bad. I think it's kind of cool structure to know about. Obviously, not something you would want to implement yourself, right? And it may, well, you'll be famous if you come. So again, so spatial locality, right? So future access will likely cluster. So you know things, right? Right. So if you access future access will be kind of close to each other, then you'll gain. So also future access will likely be to recently accessed items, right? So loops, things like that. So usually, Pareto principle, 80% of things, take 20-80 principle or 10-90-10 rule, right? So things you do, the actual things, right? 10% of the work actually, 10% of the code accounts for 90% of the time, spent. It's like in general life principle or 20-80 principle, right? So again, we guarantee these recently accessed items. So it will be interesting to see actually who is, maybe during the break I will check who is using, which products use Splay Trees. Of course, it's not advertised, right? This is like a low-level implementation detail, right? But kind of cool. So, but how do you do it, right? So they use something called zig, and zigzag, right? So zig is basically what we already seen, left, right idea, right? So single rotation, we only know about these single rotations, right? We only know from AVL and red black trees, so this is principle that we keep the binary search tree. The only thing we care about is whether, when we make rotations, whether we keep it as a binary search tree. It has to stay a binary search tree, right? You don't want to break it in the middle, right? So to do zig, X, I really don't like this. Why do they use GX? I don't know what they stand for. I wonder now. Goal X. That's what we are rotating, right? So it ends up like this. Zig. Oh, no, that's root. R is root. Okay. Zigzag, right? Oh, okay. So here, right? I guess XPG. Yeah, that makes sense, right? Zig is basically this, right? XPG, right? Let's double check. Let's see if this is correct. Let's start. Let me insert things, right? So 10, insert, and I guess 8 and 6. Yeah. Okay, let's do 8. Yeah. Okay, and 6. All right. Now, and I will find 10. Yeah. Okay. Yeah. So yeah. Okay. So basically, if you have zig situation, you sort of flip it over, basically, right? X moves up, and G goes down. That's the one zig operation, basically, right? That's one case. There's a root case, basically, right? Whatever. So X is what we are accessing, finding it, right, or inserting, right? So you rotate here, right? Root and zig again, right? Now ABC, right, and C here, right, stays. Notice, right, X takes on A from the root, and B goes to the X. Does this make sense? Let's see. X, right? Yeah, it was smaller than. Does this actually make sense? This is a little bit. Okay, so A is correct, C is correct, but here, this number here, it should be Let's see. How could B be? Well, okay, yeah. How can B be both less and more than X? That sounds a little bit suspicious here. I wonder. Root, or maybe these are just basically leaves, with empty leaves, maybe, because this looked because basically that sounds completely correct, right? And C also sounds correct, but this B, issue of B, right? Because here it's less than, right? Less than X. How can it be both less and more than X? That's something a little bit iffy. Or maybe it goes, I don't know. Well, something to be a little bit to explore more. So, but zigzag, right? So you have two zigzag situations, and basically then you have end up x again. Remember, in all cases, x ends up at the spot, right? Right. I guess you need, of course, x should go up top. I think that's the problem. Yeah, I know. Okay, that's it. Yeah, root. This, I think this is a typo here. Yeah, I think here you don't have single operation because you have to change to x is going to be the root, right? Yeah, then it's correct. Yeah, then it's correct. Yeah, this is a typo. Basically, they have made that this should be r and this should be x. Yeah, that's it. See, we found it. You know, don't trust all the materials, right? Don't trust. Yes, this is actually x. So if I can edit here. I can draw. No, I can draw this. Yeah, this one. So this is. Oh, come on. No. Oh, here we go. Type text dot circle around. What is this? All right. What's the position is drawing? Highlight, underline, strike through, add a comment, attach text. Insert text. So this would be x. What can I do x? Oh, come on. I guess here. I don't know what's happening here. Oh, delete it. I want text, type text. Okay. So x. And this would be r. This would be r, basically, right? All right. Okay. Otherwise, stays the same. Now, so finding. Let's look at the finding situation. So if you find something, right? You're looking for one, right? So zig. You see, now look what happens. So first you have a zig, right? That's a zig. I think this is another zig, right? I believe. Let's see, go move up, no, or zig and zag, I guess, right? Yeah. So now we have, well, move one up. This is almost finished, right? This is zig. I think is this zig? Yeah, it's zig. Okay, zig, right? But how does it? One moves here, and how do we attach the children? Basically, that's the question, right? 4, 5, right? And because this one is really easy, right? 2, 3, right? Here it's not so easy to understand this operation. No, it's actually zig, basically, right? And of course, last one is easy, right? 1 moves up, right, and 6, 7. So yeah, so they spend a lot of time on these operations, right? The result of 3 is this. So find again 3 moves up, zigzag, right? So again, as you find more things from the bottom, actually it will look more balanced. Now, what else? Yeah, so worst case, right? You always look for the deepest ones, right? Yeah. So the thing is, yeah, so this is the thing. So this is what their genius, I guess, was that if you try to make it bad, right? If you start accessing, so as you start accessing the ones at the bottom, your tree will actually become like your splay tree will look like a good, nicely balanced binary search tree. So that's the beauty, basically, right? So yeah, if you keep accessing things at top, it will look unbalanced, but since you are doing the getting the top items, doesn't matter. As soon as you start making these evil choices, so as soon as you turn to the evil side, right, try to get the bad choices, your tree will start balancing. So it's kind of like, yeah, so kind of like reverse, I don't know, psychology or reverse idea. So yeah, if you want to make it look bad, you'll actually make it good. So and if you want to make it good, right, it'll look bad. So let's do this again one more time. So let's see 12, right? Insert, right, and I'll do so 14. So again, if I want to make it, so let's look at the most extreme cases. So if I'll do 16 as well, right? So if I keep looking for 16, right, it will stay bad, right? Because 16, yeah, or 14, right? 14, 16, 14, 16. Right? Let's do a search for 14, right? It will not make a big improvement, right? When I do for 16, right? So looking, so okay, so here's the thing. So looking for the only few things will make the tree look bad, but you have the good access. But as soon as you start being evil, right? So 6, right? Find 6. right? We know it's going to be bad. Now look for 8. Right? Now look for 10 at the bottom. You see? Now look for 14. See, now it looks like 3. So 8. So I'm trying to be as evil as I'm basically I have this I have a genie who tells me which things to look for, right? And 12, right? I keep looking for the deepest thing possible, right? And it's now, look at this. I made like the worst possible choices, but I end up with actually a good 3, right? So by making these bad choices, right, I actually end up with a good 3. And then I get this log n, which I wanted also, right? So either I have a really good access, right? Or I have by making it bad access, I end up with a good 3, right? So, so this looks like the devil cannot win basically with this Splay Trees. I guess that's the takeaway basically is, right. So no matter how bad I try. So I suppose again it's been proven that if you try like be somewhere in between, maybe alternate between approach, try to get more frequent ones. But okay, again if you keep getting 12, that's good. I mean, hey, it's constant, right? But if you start doing something in here, it will still be log n. So that's how white works actually. Right. So even if you try to be as bad as possible, it will still be good or decent. You know, log n is considered good, or almost excellent. To me? Thank you. So, all right. So that's the worst case, right? So again, by insertion, so insertion, right? Yeah. All right. Okay, insertion. Again, so we see it always starts with, well, insert, find the right place, and then basically play up top, basically. Deletion. Again, start at bottom, right? Find the right place. We always find the right place using binary search tree, right? And then use play, do this play operation, zigzag, zigzag, up top. Right. Go ahead, this. Right. Yeah. So again, by trying to be evil, we still can't be evil, right? So we have, what kind of operations we have? Insert, of course, find x, right? Delete minimum, delete maximum, remove, right? So removing x, right? We can overwrite as well, right? So those are operations. Let's see what we want to do, right? So top-down splaying, right? We can also prune the other approaches, right, by splaying up. Let's see what else. Yeah, we can do. But again, I'm not going to go in detail right now. Right, there's too many of these operations. Not possible to do this in a single lecture, right? So you have to, if you want to study this more in detail, right? So again, but the summary is that again they adjust, self-adjusting trees, right? So basically, right. So what I want to show, let's see what we have. In the second part of the lecture, we'll look at the actual implementation. But then we have a couple of structures. Yeah, skip lists are really cool, and try data structure, which will be next week, I think. So yeah, that's, I think, is the skip lists are kind of cool as well. But again, they of course become more aesthetic. I guess let's few more minutes. Let's find out who uses Splay Trees. Usage of Splay Trees in industry, right? It's kind of hard to find, of course. Well, yeah, you can. These are the official, right? Yeah, real time. This is like 6-7 years ago. I remember right. Yeah. So, like I said, not a good match for data which rarely changes, right? Yeah. Oh, there's SplayNet or something like that, some sort of network thing. Yeah. Real life, right? Somebody tried to use autocomplete. Some ambitious student. No, it doesn't have any answers. Actually, it's not. This is old answer.
Maybe because nobody uses them.
Yeah, nobody uses. Yeah. So Quora again. This Core used to be decent, not anymore. I don't, Core is basically a garbage fire right now, but still, right? Yeah. Yeah, right. So the answer, but where actually, right? actual real life application which use this, right? So everybody says these are like bot, right? This is actually, oh yeah, core use AI answers now, of course, right? Which is kind of semi useless, you know, right? Dictionary. Yeah, this is bad. Okay, so this is challenge. Find actual real life usage. All right. So let's take a break. Actually, continue around 12. We can finish maybe a little earlier today. So let's continue at 12.